Hi Year 12, this is our third lesson for the topic of further differentiation. In this lesson we're going to look at combined functions. So far this topic we have learnt about the derivative of trig functions, the derivative of exponential functions including bases other than e, and the derivative of log functions also including bases other than e. So recall that there are three rules that we use for combined or composite functions. There's the chain rule, the product rule, and the quotient rule. Let's start with the chain rule, which is used for composite functions. So f of g of x is given for you on your reference sheet. So it says the derivative of a composite function f of g of x is equal to the derivative of the outer function, so f dashed of g of x, multiplied by the derivative of the inner function, g dashed of x. Let's look at an example. Suppose we want to find the derivative of y is equal to ln of sine x. I always teach my students to identify what the outer function is, which in this case is log base e, and what the inner function is, which in this case is sine x. So we have a trig function sitting aside a log function. So when we go to do the derivative, we want to differentiate the outer function. Now log, remember log base e, that's going to be 1 over whatever is in these brackets here, so 1 over sine x. Then we're going to multiply by the derivative of the inner function. The derivative of sine x is cos x. And tidying that up, I get cos x over sine x. You can leave it like that, or we could write it as cot x. Let's try another one. If f of x is equal to cos x take away 1 all cubed, find the value of f dashed of pi on 3. So the inner function is cos x take away 1. The outer function is a power rule. All right, let's do the outer function first. So the 3 comes down. Leave this alone to the power of 2, multiplied by the derivative of the inner function, which is negative sine x. And tidying that up, we get negative 3 sine x cos x take away 1 all squared. Now, if we want to substitute in pi on 3, we're going to get negative 3 sine pi on 3, and then in brackets cos pi on 3 take away 1 all squared. And we're going to need to use our exact values here. Sine pi on 3, remember that's sine 60, so that's root 3 on 2. And cos pi on 3, so that's cos 60, that's a half. A half take away 1 is negative a half. Right, what have we got here? We've got negative 3 root 3 on 2, and then a half take away 1 all squared. And so tidying that up, we get negative 3 root 3 on 8. Moving on to the product rule. It's used when we have the multiplication of two functions. So we might have y is equal to some function of x multiplied by another function of x. And in this case, we'll call the first one u and the second one v. Then dy dx will equal u times v dashed plus v times u dashed. Now it is given for you on your reference sheet, but it is in a bit longer form. So instead of v dash, they've written dv dx, and instead of u dash, they've written du dx. Here's our first example. Given f of x is equal to x cubed tan x, find f dashed of x. So we can see that we've got a product here. We've got x cubed multiplied by tan x. So I'm going to make u equal to x cubed and v equal to tan x. And I'm going to write those down. Now let's find the derivatives. U dashed will be 3x squared. V dashed will be sec squared x. Now the product rule is very easy to construct. All we're going to do is u multiplied by v dashed plus v multiplied by u dashed. And we can tidy this up by taking out common factor of x squared. And that's it, x squared outside of x, sec squared x plus 3 tan x. Here's example 2. When is the gradient of the tangent to the curve y equals x e to the x cubed take away 1 equal to 0? Gradient of the tangent is the first derivative, so we want to differentiate this, and we have a product rule. We can see we've got x multiplied by e to the x cubed take away 1. But furthermore, e to the x cubed take away 1 is actually a composite function. So we're going to need to use the chain rule for this part. So this is where it's really important that you separate the u and the v out and work out the derivatives nice and logically in your working out. So u is equal to x, v is equal to e to the x cubed, take away 1. Derivative of x is 1. The derivative of this, right, our outer function is an exponential, our inner function is a power rule. So differentiating an exponential, e, is just the same, so it stays the same, multiplied by the derivative of this inner function, which is 3x squared. Take the time to tidy this up. Now let's construct the product rule. So dy dx is equal to x multiplied by 3x squared, e to the x cubed, take away 1, so that's u multiplied by v dashed, plus v multiplied by u dashed, which is e to the x cubed, take away 1, multiplied by 1. And tidying that up and factorising, we've got e to the x cubed, take away 1, and then in brackets 3x cubed plus 1. And finally, the quotient rule is used when we have a function divided by another function. So we might have a function of x, which we will call u, divided by another function of x, which we will call v. Then the derivative will be v u dashed, take away u v dashed, all over v squared. And again, on your reference sheet, it is written in a more formal manner. V du dx, take away u dv dx, all over v squared. Now, one thing to be careful of with the quotient rule is the order, because it starts with v, unlike the product rule, which starts with u. Here's our first example. Find the derivative of log base 2 of x all over 1 minus sine x. So we can see here that we have a quotient rule. We have a function in x divided by another function in x. So we're going to call this one u and the bottom one v. Take the time to list these out and work out the derivatives. So the derivative of log base 2 of x, we need to go to our reference sheet. A is 2, f of x is x. So the derivative will be 1 over ln 2 multiplied by x. Now I've turned that around so there's no confusion. The derivative of v is 0 take away cos x. Now let's construct the quotient rule. So we want v, make sure you put this in brackets anytime there is more than one term. V multiplied by u dashed, take away u multiplied by v dashed, all over v squared. Don't expand the denominator, just leave it as it is. All right, the numerator is a bit of a mess. We need to sort that out because we've got double-decker fractions at the moment. So just tidying it up a little bit, I've got 1 take away sine x all over x ln 2 plus cos x log base 2 of x. Now this needs to have the same denominator as this one. So I'm going to multiply top and bottom, remember this is over 1, top and bottom by x ln 2, like this. Now this is just division of fractions, so I'm going to take this numerator, divide by 1 minus sine x all squared, which is the same as multiplying by 1 over 1 minus sine x all squared. So we end up with this, and that's actually the answer. Have a look at the top here, 1 minus sine x plus x ln 2 cos x log base 2 of x. This x ln 2 kind of falls through the floor when you do this division of fractions. So on the denominator, I've got x ln 2 multiplied by 1 minus sine x all squared. Okay, that was a bit hard, that question. Let's see if we've got an easier one to keep going with. Here's example 2. Consider the function f of x is equal to 2x over ln of cos x. Find f dashed of x. So u is going to be 2x, and v is a composite function, ln of cos x. So let's take the time to write them down and do the derivatives. The derivative of u is easy, that's just 2. The derivative of v, we have an outer function which is log base e, inner function which is cos x. So the derivative here will be 1 over cos x multiplied by the derivative of the inner function which is negative sine x. Tidying this up, we get negative tan x. So constructing our quotient rule, we have v, which is ln of cos x multiplied by u dashed, take away u multiplied by v dashed, all over v squared. Just leave this as it is, don't try and expand it. And all we have to do is just tidy up this numerator. So we get 2 ln of cos x plus 2x tan x all over ln of cos x all squared. And we'll finish off this video with just some applications. So recall that the derivative is the gradient of the tangent to the curve at the point x. We can use calculus and coordinate geometry to find the equation of a tangent to a curve. So here's an example. Find the equation of the tangent to the curve y equals ln of x squared plus 1 at the point 1 ln 2. So we can see here that we have a composite function. So we're going to need to use our chain rule to get the derivative. So y dashed will be, our outer function is log base e, so 1 over x squared plus 1, multiplied by the derivative of the inner function, which is 2x. Tidying that up, we get 2x over x squared plus 1. Now we want to substitute in x is equal to 1 so we can work out the gradient of the tangent. So at x equals 1, y dashed is equal to 2 over 1 plus 1, which is 2 over 2, which is 1. So we have our point and we have our gradient. We're going to go into the point gradient formula. Y take away y1 is equal to m, and then in brackets x take away x1. Now we want to leave this in exact form, so I'm just going to expand brackets and then tidy that up as best as we can. So y will equal x plus ln 2 take away 1. Now we can also work out the gradient or equation of the normal. And remember, the normal is perpendicular to the tangent. Find the equation of the normal to the curve y equals sine x take away cos x when x is equal to pi on 4. So we'll start again with the derivative. So y dashed is equal to cos x take away negative sine x, which is cos x plus sine x. Now we need to work out the gradient of the tangent at x equals pi on 4. So substituting in. At x is equal to pi on 4, dy dx is equal to cos pi on 4 plus sine pi on 4, which is 1 on root 2 plus 1 on root 2, which is 2 on root 2. Now that, of course, is the gradient of the tangent, not the normal, but the normal is perpendicular to the tangent. So to work out the gradient of the normal, we just do the negative reciprocal. Now I want to use the point gradient formula. I have the gradient, but I've only got the x coordinate. So to find the y coordinate, I substitute back into the curve. At x equals pi on 4, y is equal to sine pi on 4 take away cos pi on 4, which is 1 on root 2 take away 1 on root 2, which is 0. So now I have all the information that I need. I have the gradient and the point. So into our point gradient formula, y take away y1 is equal to m multiplied by x take away x1. Expand through the brackets here. I end up with negative root 2 on 2x plus pi root 2 on 8. And I just need to get rid of this 0 and we're finished. So y is equal to negative root 2 on 2x plus pi root 2 on 8. Okay, that's it for this lesson. Our last lesson for this topic is on anti-differentiation.